it might be. And the idea is that we can have these specialized interrogators, which contain lasers that, a billion times a second fire short pulses of laser light down the length of the fiber. And fiber is not a perfectly transparent quantity, so there's some impurities in it that cause some backscattering of light energy back along the fiber that's actually recorded by the interrogator. And so the idea is that we can look at the signals coming back from the interrogator. And basically, that's ideally going to be looking like seismic data. Now, if you have a fiber that is not strained, it's just at rest, then if you keep firing pulses, then you'll get a static pattern coming back along the fiber. However, if you have an acoustic pressure disturbance coming in like this, what this effectively does is, in a very small sense, it strains the fiber, which basically increases the length of the fiber, which then changes the pattern that comes back here because you have a longer distance to actually travel. And so what we're actually measuring in this case is deformation rate, which there's quite a bit of background noise. There might be some need to mute signals in the background. In this case, we're measuring the deformation rate, or the rate at which the fiber deforms, which in this case is you basically integrate from 0 here to X, the point of observation, and you're effectively measuring the strain rate along the fiber. And so what we want to do when we actually have the data is we want to process it in order to make an estimate of the strain rate. And this is the quantity that we're going to be looking at right here. So the time rate of strain. And the idea here is that if you have a measurement of deformation rate at a sensing point plus half what's called the gauge length. So here, you can subtract that off the measurement here at half the gauge length on the other side, divide by the gauge length. And that's how we actually recover an estimate of the strain rate. And that's what we're going to be looking at today. So there's a couple of quantities in here that are very dependent on the interrogator system that we're looking at. Sorry, there's a lot of background talking.
No, but now you can connect it. It won't give that problem yet.
Oh, okay. Sorry. Sorry, there's quite a bit of background noise. Would people be able to? Thank you. I think that's better. Great. So what does this look like in practice? And this is a data set that we were able to require when I was working at University of Western Australia previously. And so here, for referencing you, this is the country of Australia, and UWA is at Perth, here down in that the far southwest corner. And what they did at this university for another experiment, they put in 80 kilometers of an optical fiber loop that goes around like this, and this goes to and from the campus of UWA. And so we were able to get access to this, in particular, a short section of this, about 15.6 kilometers. And we were able to do some initial tests of DAS interrogator technology. This is about 5 or 6 years ago when we were able to get the data. And the idea is that we were able to access the fiber array here, and then be able to pulse light all the way down sort of 15 kilometers through this urban environment in order to be able to see what types of signals that we were able to acquire. And so here we have an initial segment. The first half of it is a residential area, so it goes through quiet residential streets. But after that, it gets into a commercial area right down here where there's a lot more traffic. And so we can look at what the DAS data looks like. And in this case, just to reference you, here we are, we're looking, the vertical axis is time. So that is, about a minute there worth of data. And here we have a dense recording along about 15.6 kilometers of fiber. So each one of these is sort of like your standard seismic trace that has all been put together. And in this area here, where it's quiet residential, there's not much going on. We don't really see much of this strain rate energy happening in this location. But as we get over to the commercial area, we can see that there's a lot more signals. In particular, sort of as we come into the commercial area, we start seeing this vertical banding here, which is a stationary vibration source. We also see some dipping energy that looks like this. And these are actually, if you measure the distance over time, you see it's about 350 meters in 20 seconds, which you can calculate that 63 kilometers an hour. So that's actually a heavy truck that's moving along the road. And we also see as we get to the very end of the recording, we're getting to the limits of what we can see within the optical fiber. And so we can clearly see a lot of interesting features in the data, but we can actually go one step further, and I hope this plays for you. In this case, we can actually take the DAS recordings and sonify them. And what I mean by that is turn them into sound wave files that we can actually play and listen to. So the first one here is just someone doing a tap test. So this is taking a sledgehammer above where this fiber is installed, and I should say that this is installed just in PVC conduit about 50 centimeters under the ground. And what we're tapping, we're going to listen to the natural vibrations that are caused by that. All right. So the next one is we get into the more traffic area, and what we can listen to is actually cars driving over potholes. And I'm sure we've all heard this. The next one we're listening at is there's a train station here for local commuter rail. And what we're listening to is the train coming into the station. And the final one here is that we have a truck that is currently at a stoplight here. And once it turns green, then you hear the heavy truck starting up. So just vibrating. So we can clearly hear a lot of interesting things going on within the DAS fiber, but can we say something, use this information to say something informative about the Earth? And what we're looking at here today are two different studies that I put together to showcase sort of some of the breadth that you can expect from the applications of DAS. And the first one is looking at low frequency ambient seismology. So this is signals that are less than 2 hertz. And here we're going to look at some of the observations that we have. We're going to talk about seismic interferometry, and then how we take the results of seismic interferometry and use them in one-dimensional multi-channel analysis of surface waves in order to estimate something about the Earth properties in the subsurface. The second one is looking at building a DAS land streamer for more geotechnical problems. And here again, we'll be looking at a number of different things within that. So in terms of the first study, this is a collaboration that went on after when I was just leaving and after I left Western Australia. And so this is with a PhD student of mine, Ji-Hoon Yang, as well as 2 principals of the Terra 15 company, which is a manufacturer of interrogators, and as well as 2 people at the University of Western Australia. And the story begins with sort of an opportunity to collect some interesting data one night. So in this case, there was a big storm that was coming into the Perth area, and our partners at Terra 15 thought it would be interesting to go out and acquire snapshots of just the ground shaking due to storm action, sort of 1 minute every 10 minutes for an entire evening. And so what we're looking at here on the left is the low frequency DAS data. This is between 0.04 hertz to 1.8 hertz. So this is like your seismic data that we're talking about again. So 15 kilometers here and a minute worth of recording. So a dense panel. And in this, we were able to do some denoising activities. So this is separating sort of signal in here. And this is our noise estimate on the right to generate signals that look like this here in the middle. And it doesn't look like much other than maybe you can see sort of things that are dipping, from right to left across the array. And in this case, I'll just sort of draw some dotted lines there to emphasize sort of the general trends of what I'm talking about. So this is something acquired at 7:30 at night. We can then do, recordings later on. This is at 8:10. We see similar sort of dip structure. And then 11:10 at night, and again, we see similar sort of dip structure going down like this. So we have some feature that's happening in the Earth that is repetitive, that's going on for hours and hours and hours and hours, that has some information about the Earth. In particular, the rate at which they're dipping is, depends on the Earth's velocity profile. So ideally, we'd be able to process it to understand that. And in fact, what this is here is this is actually swell noise. So if you've ever been down to the beach from the African Ocean, just like here in the Indian Ocean, if you have a big storm that comes on, you have basically wave action that comes basically from the deep water to the shallow coast, hits the coastline, and in this case, you actually get Rayleigh wave energy generated, potentially love waves, but predominantly Rayleigh wave energy generated as the waves come ashore, interact with this, and then those propagate into the actual, into the land. And so what the question we were looking at here is, how can we use these signals to better understand the Earth? Now, the data that we're looking at is just these dipping lines, and it's pretty hard to sort of understand how we might do that, but actually through the process of seismic interferometry, it allows us to generate something that looks like active seismic data. And that's where we're going here with this brief discussion on what seismic interferometry is. So let's say we had a Rayleigh wave energy source here that might be in the ocean. It then propagates here, hits the receiver A. So this is like either a DAS cable or a seismic geophone, and then propagates, and the saved waveforms hit B. So in this case, if we look at what we'd expect in sort of the time traces going down here, we would have the disturbance start hitting A, finishing up, and then a little time later, we would see that arriving at B. And then it would be sort of a similar waveform that looks like this. And what we can do with these waveforms is we can use the power of cross-correlation in order to make some informative about the relative time differences between when the signals arrived at A versus when the signals arrived at B. So in this case, we know that if it takes this one here, and then it takes a delta T later, it arrives at this station. By going through cross-correlation, we can develop what is called an interferogram, which basically says, okay, we go here and we see that there's a spike here at a delay time of delta T. And I think the real insight into interferometry is that even though we have these ambient recordings, what this one looks like here in the interferogram, it's like there was an active source going off at A that then delta T times later, it arrived at delta B, arrived at B. So can we do this in the opposite direction? And the answer is yes. So if you have a source, say on this side, this waveform travels, hits B, and then goes to A, then we have something that looks like this. So here we have now B to A. In this case, we'll have to shift A delta T in this direction here in order to get the overlap of these two signals. And so this generates an interferogram in the opposite sense. And so if you have now many, many sources that are going on here on this side of A, then what happens is that you basically see the energy going from A to B.
Jeff,
And those, yes.
sorry for the interruption, but we can't see your pointer.
Oh, you cannot see my pointer. Interesting. Can you see it now?
Yes.
Okay, apologies for that. Thank you for letting me know. So if you have a number of sources here that come to A first and then go to B, you can develop a response here at A that basically looks like this. So this is the waveforms that are coming in. If you have now a number at B that are going this way to A, then that lets you to develop the response on this side at the negative time lags. And so now what we can do is we can say, well, if we have, this is the main receiver that we're actually going to be correlating all the signals at all the other stations with, then what happens is that here at station A, which is located here, if you do this for enough time at enough stations, you can start developing something that looks like this. And this is known as a virtual shot gather. And in effect, what that is that you're obtaining the empirical seismic response of what a source would be at A through cross-correlation stacking all across the array. So what we're aiming to do through this is to be able to generate things that look like this, which look like active shot gathers, that we can then use for our various seismic data processing activities. And in this case, just showing a little bit of the mathematics of what we want to do here. So the seismic interferometry process through cross-correlation is represented by this equation here, where if you have the wave field here, and this is the frequency domain, so this is the Fourier transform of this waveform here, located a trace at x1. You take the complex conjugate of that, and then you multiply it by the data and the frequency here at a location x2. You then take the inverse Fourier transform of that. That allows you to develop this cross-correlation interferogram here with these time lags. This is the inverse Fourier transform. This is correlation lag, and these are the two locations. This is for a single panel, but then you can stack over many, many different panels over a number of times and allow you to generate images like I was just showing. We're also going to be looking at deconvolution, which is a related type of processing. In this case, the numerator of this expression here is the same, but in this case, we're just going to normalize this by taking the magnitude of both of the traces, dividing that out, which helps to do sort of spectral balancing. And then this is just a stabilization parameter. And so if you do this for, in this case, 32 minutes of total time, it allows us to generate signals that look like this. So in this case, we have the interrogator that's located at the campus. This is the array along here that we were looking at. And here's going to be the receiver that we're going to use for all of the correlations. And we're going to correlate that with the wave fields recorded all along these locations here. So at this point here, this is that pink star. So this is the location that we're using for all the correlations. And what we see here, this is in terms of time lag. This is zero time lag. This is sort of negative time. This is positive time. And what you can see is that we can now see waves that are propagating away from this station here. And these are in fact some surface waves, some Rayleigh wave energy that we were able to just use this seismic interferometry process in order to be able to make images of. So this is with cross correlation. This is with deconvolution. In general, hopefully you can see that there's, you get a little bit more resolution with deconvolution. However, it does also bring up sort of the noise. So I'm going to just show both of them for the next few slides. So this is as if we had an active source set off at this location here, about 2.5 kilometers along the array. Well, then we can just go along the array. And here's another one at 5.2 kilometers. Again, similar sort of thing. In this case, we see energy going back towards, this is the zero, this is the end. We see energy going back towards this and also energy radiating out of that. In this case, if we come along here, we see these X patterns, which again are waves propagating away from that virtual source location. And then by the time we get to the end here, we see that in this case, the signal is getting pretty noisy, but we still can make out some of these faint arrivals across the array. So overall, we're able to do a fairly good job of using or developing these virtual shot gathers, and I can just play a movie across all of these just to show the types of data that we can actually get by just, again, this is just fiber that was put in the ground for another purpose, and all we're doing is we're putting the interrogator on campus at UWA, sending photons down the fiber, listening to the backscatter, and through some interesting processing, we're able to recover these estimates of wave propagation at each one of these sites. Now, here, there's also some interesting things that there's varying quality as you go along the fiber. And one of the issues here is that as you start getting lots of kinks in this, and as you start getting sort of the fiber-oriented north-south, then you start losing some of the sensitivity. So in this case, we're going to be looking at only a short section of this fiber, where we have a nice straight 4-kilometer section here, and we have wave energy then that hits the coast here and then propagates largely to the east in this case, and gives us the basically waves largely in line with the recording array. And this is the data that we'll be looking at. So these types of arrivals along this straight section right in here, and we want to analyze these waveforms here to see, can we make an informative estimate of what the Earth's shear wave velocity is beneath that part of the array. And so the approach that we're going to use for this is known as multi-channel analysis of surface waves. And this is used for the last sort of 25 years in the geotechnical community to make informed estimates about the one-dimensional shear wave velocity structure beneath seismic arrays. And the idea is that you want to invert frequency-dependent Rayleigh wave arrivals for imaging and characterizing the subsurface. And this work largely comes out of the classic paper of Park et al. At the Kansas Geological Survey in the late 90s. And the idea is that if we have data that's acquired in linear arrays that have equally spaced channels like this, so normally it's been geophone data that we're looking at, we have active source that goes off here. So if we have a spread of length L, what this MASW technique allows you to do is to say, if we have, let's say, a layered Earth model where we have, in this case, 4 layers of H are the thicknesses of the layers, and the VS's are the shear wave velocities of the layer, we can then use this information in order to see what the layered velocity structure is in this area. So this is a fairly robust to noise. It's fairly easy to implement. There are a number of codes that are out there if you are interested in doing such an approach. But it does require aligned sources and receivers, and it is limited to 1D layered model inversion. But we'll look at a little bit different in just a minute. And so here in this section here, we see that we actually have a fairly good linear array that we should be able to use for MASW. And so in this case, there's the 2 steps. One is doing the Rayleigh wave velocity analysis. And this is the data that we're looking at, and this is in the distance and lag domain, so time and space. And what these dispersion images are is basically, it says you can do transformations that allow you to take this data and represent it in a panel that is a function of frequency on this axis, and then the phase velocity on this axis. And so the idea is that as you go to lower and lower frequencies, Rayleigh waves are sensitive to deeper and deeper structures. And general, because the velocity of the Earth increases with depth, you expect that these to actually kind of go upwards. And in this case, what you would do is you'd say you'd want to pick kind of the hot points on this dispersion curve and be able to use that for the next stage of inversion. But this is sort of not the best one. So there's other approaches you can do. And here we follow some of the work of Dylan Mikesell he was at Boise State at the time, and he was looking at how do you sparsify these images to more clearly show the dispersion trends. And so hopefully you would agree here that this is sort of this is the Rayleigh wave fundamental mode. And in this case, you would want to pick the curves at these white locations here, and those would be the data that we would want to use in an inversion process. So these white dots are effectively for each frequency that we're looking at, that's what we're going to look at for inversion. And in this case, we're going to use the MASW waves package. And this is with Ólafsdóttir, so they're from Iceland, and they have a really nice open source package that I see many people are using all around the world. And the idea is that if we have measured data here, so these would be those white dots from the previous example, and those are the red asterisks there. We want to be able to say, okay, given that layered Earth model, which is the thicknesses and the shear wave velocities, are we able to forward model data that effectively matches those dispersion curves? And in this case, you can think about setting up your forward operator, and this is just the Thompson-Haskell matrix, for those of you who are aware of how to forward model frequency-dependent Rayleigh waves. And in this case, we see that when we do this, our initial model is off quite a bit. And so we have to think about how do we go through an optimization process such that we're able to better match the data. And the MAS Waves package implements what's called particle swarm optimization, where basically it intelligently samples a wide variety of the possible solution space and then comes up with an estimate of which models best fit our data. And in this case, we're showing the results from, we tested overall about 14,000 different models through particle swarm optimization. And what we're looking at is we're showing here, the green ones are the 10 best fitting lines, and the blue one here is our best fit line. And so what the data are telling us at this location is that we have a fairly fast, shallow layer down to about 150 meters. The velocity then drops down to a slow layer, just over 1,000 meters, and then it speeds up quite a bit to around 3,000 meters per second. In this case, we were fortunate enough to have borehole data, sort of less than 3 kilometers away, which allows us to examine how do our inversion results from the DAS recordings, how do they match with other observations? So in this case, we have 2 bits of information. One, we had sort of a lithological log that was recorded. And what we have here is we have the Tamala limestone, which is a fast, competent material that overlies poorly lithified sands with minor silts. That then overlies a lithified sandstone with interbedded siltstones and clays. So here we have fast, slow, because it's poorly lithified, and then quite a bit faster, because we're now deeper and have better lithification. We also have gamma ray logs over here, which then shows about this location, 100 meters, we see a kick down, and then down here we see a big kick up around 550 meters. And if you look at sort of the inversion results here, we see again, we're picturing a log, or we're picturing a layer somewhere around sort of 160, 170, drops down, and then we predict a big pickup right down here about 550, which is consistent with some of the log data. So overall, we have a plausible fit to the data that we've recorded. And I think what's really interesting here in this example is that this was just, again, fiber that happened to be in the ground. We happened to be able to listen during a storm where there was a lot of energy generated at the coast. We could make these low frequency ambient seismic recordings and use seismic interferometry and MASW in order to make an estimate of the physical properties of the Earth. So I'd like now to change gears and talk about the seismic land streamer, and again, how we can think about using distributed acoustic sensing in a slightly different way that is applicable for near-surface seismic challenges. And this is some of the work of Adesh Pandey. So he's one of my PhD students at Mines, another PhD student, Derek Chambers, and a research associate, Aaron Gerard, all within our Center for Wave Phenomena. And in terms of near-surface challenges, there's a wide variety of things that we want to use geophysics and in particular seismic in order to investigate. Some of them could be buried object detection. So this is motivated by an example where in this case, they had a bridge and they want to put in a new bridge. They have footings that have been put in the ground, but they also know that there's voids in the area. So how can we use geophysics to try and know in advance where those void locations are, so we don't try and build bridges over voids, because that would be very uncomfortable. We also have situations where we have infrastructure that we like to evaluate. In this case, they want to build a brand new facility, And so geophysics is often used to make estimates of the top 30 meters of soil, sort of VS30, which then that allows us to see what type of engineering designs do we need to do from a civil engineering perspective. Another one that's quite important is assessing shallow geohazards. And this here is obviously a rock fall that has closed off a highway. And in this case, geophysics, of course, isn't going to stop this from falling, but we can characterize why this rock slide happened and then make informed estimates about what is the hazard of it occurring at other parts along the road here. And so this is where sort of seismic methods actually can be very, very helpful. So in this case, what we do normally in near-surface seismic acquisition is we have a source that goes up here, and we have often equally spaced receivers that look like this. These are then recorded by a seismic acquisition vehicle. This is your spread size, and the idea is that we often want to roll this spread along, so move it in this direction as we laterally sample the Earth from left to right. And sort of similar to before, if you do this in a certain way, you can get a really nice estimate of your surface waves right here. You can then go through MASW or other inversion techniques that allow you to make sort of shear wave velocity profiles that look like this. And if you're able to move that spread along and repeat your analysis, you're able to start making nice two-dimensional maps of the shear wave velocity structure. This is a nice example from, I believe, the Kansas Geological Survey that shows the lateral variations in high resolution within the top meter. Some of the challenges with this is that it requires significant cabling, other instrumentation. It's challenging to roll along, time-consuming, manual, labor-intensive. And because you have to use, in this case, geophones in the ground, it has limited spatial sampling. And so, a few decades ago, some engineering seismologists decided to try out a land streamer design, and this is sort of modeled on the types of streamers that we have in marine seismic, but applying it to land. So the idea is that if you have a vehicle that can tow some sort of structure, you can put geophones on here and basically have a more mobile array that allow you, once you excite the energy, to basically get the response at that location and then shift the entire array along. And to give you an idea of what this looks like, this is a nice example from colleagues, I think, at Uppsala University, where they required 650 line kilometers of this at a 10-meter shot spacing. And what we're looking at here is a vibra-sized truck pulling this array. So I'm just going to do a bit of a movie there. So it goes in there, and you can see that it's towing the array along as it's vibrating, picks it up, moves it along, and then records all the signals. So they did this for about 650 kilometers and had some really high quality results. So using a land streamer is actually quite beneficial because you can easily roll that spread of seismic cables and be able to create two-dimensional profiles of your shear wave velocity structure. And it's not that consuming. Once you basically put it out, they were able to just, for a number of days, just be able to go and acquire the data. Although one thing is that it does require significant cabling, other instrumentation, and you are limited to the spatial sampling that you have in your geophones. So what we're interested in doing is how can we think about applying distributed acoustic sensing in place of some of these design features that we have in geophone land streamers. So here we have just the schematic of your land streamer. We have all of these geophones out here. You have your seismograph and you have your impact source. So the key idea here is that we want to replace your seismograph with an interrogator and just have a fiber that lies along the ground. It looks like that, listening in very, very dense, densely along the array to what the ground vibrations are doing. So in this case, this is sort of a couple features, a couple snapshots of the prototype that we put together. So our model here is that we have a fiber here that we put just fire hose on top of that. And the reason why we put fire hose on that is that it forces it down on the ground, which gives better coupling to the ground. And it also shields it from environmental factors such as a wind and other noise sources. So it proved in earlier tests to be beneficial to put it under fire hose. In this case, we have a weight drop source. So this is a PEG 40, It basically lifts up and then accelerates that down. And this is our tow truck here with the United States Geological Survey. And so initially we're thinking that the advantages of this are it's minimal instrumentation. It's just fire optic cable, hose pipe, and the interrogator. It's easy to tow and roll. We get very dense spatial sampling. In this case, we get 80 centimeters between our channels that we're actually measuring, and it's rapidly rapid to deploy and allows you to do it without that much work. But again, the fiber's really sensitive to only one component of ground shaking. There are some ground coupling challenges, and of course there is the expense of the interrogator to start with. So what we're doing here is we're going to come up with a test that looks like this. So in this case, we have 72 meters of land streamer. So that's just basically the fiber in red, and this is the fire hose section that's over top of that. And we're going to compare the results to geophone that are put in the ground every 10 feet. And this fiber is going to continue here and then go out to the interrogator where we actually measure the signals. So in this case, this is what the raw data for a single shot looked like. And doesn't really look like sort of the seismic data that we'd wanted to with just this one raw gather. In particular, we see that there's this low frequency, high amplitude oscillating noise within the first 12 meters of the array. And this was actually a bit of a design feature or design fail that we didn't really think about when we were putting together the system. And as you can see here, we have the truck, this is the towing, the tow strap, and this is the bar, and this is the fiber that's coming in there. And this is actually off of the ground. So if we actually sort of look at it, we see the weight drop goes up, comes down like that, and then the entire system shakes at about 3 times a second. And you can see here, you look at this, the period of the ground shaking is about 0.3 seconds in here. So this is basically because of a fairly poor design feature. And so what we'll show you how we mitigated that in just a second. In this case, we also see that you can see in here, hopefully, that there's surface waves that are coming like this, but they're fairly weak. And there's also, in this case, a lot of salt and pepper noise that's going on here. And so we had to go through a short processing sequence that allowed us to try and improve the signal quality so that we're able to better analyze the surface wave data. So here we just have what the shot looks like when we remove the first 12 meters. And what we're looking at here, this is just the 2-dimensional Fourier transform. So this is time and space. This is frequency and wave number. So most of the dipping energy here maps right into this location here. So this is what we'd like to highlight through processing. So this was a single shot. We can then stack 5 shots together, and you can see just right there through the process of stacking, the signal to noise has improved. We can then go through trace balancing and some bandpass filtering to highlight just the energy within the band of interest. And then we can do a little velocity dip filtering to remove some implausibly fast waves from that. And by going through this entire sequence, we're able to go through a fairly noisy raw shot gather all the way through to the final processed results. And so, this is the type of information that we want to actually use in our inversions. Just to show the comparison with the geophone data, here on the left is a raw geophone shot gather, again at 10 feet spacing. We can then go through a similar processing sequence and be able to come up with a process shot gather look like that. And sort of the comparison between the process shot gather, process DAS, and the process geophone is that here we clearly have much denser sampling, which allows us to better understand the signals, the surface wave signals that are in the ground. And we can also plot these in terms of overlays. And so in this case, what we're looking at on the grayscale image beneath this is the DAS data, and we put in wiggle traces over top of that. We see the geophones. In this case, where we have a lot of these, clear arrivals in the surface waves, we see that we're doing fairly well in matching the wiggles with the geophones. So even though these aren't exactly, as we say, apples to apples in terms of comparison. Overall, we have fairly good correspondence between the two data sets. And we can then go one step further again and look at these dispersion panels like we looked at before. On the left-hand side, this is the DAS data. The right-hand side is the geophone data. And on the left-hand side here, again, this is frequency on the horizontal axis. These are our velocities with the vertical axis. And what we see here is we see these nice fundamental Rayleigh wave modes and the higher order Rayleigh wave modes that are fairly easy to interpret and pick if you'd like to do that. Whereas on the geophone data, it just doesn't have quite the signal to noise, and it's hard to see some of these higher modes. So overall, the DAS Landstreamer has been quite helpful in getting the data that we'd like. So the initial tests of the DAS Landstreamer are quite positive. It's rapidly deployable. It's efficient to use in favorable ground conditions, so compacted soil, earthen embankments, pavement. Acquires sort of comparable waveforms, and we have really nice high spatial resolution because of this the sampling that we have. And so we're looking to test this in other scenarios, and this is a project that we have up in the high mountains of just west of Denver, and this is on an earthen dam structure. And the idea is that we want to test the Landstreamer there to try and understand some of the internal lateral sort of shear wave velocity structures that are in this particular system. And so, we can use this for geologic mapping, for geohazard identification, geotechnical engineering applications like we have here. We can look at oil and gas facilities. So there's a lot of different applications. And where we'd really like to take this is to be able to take this type of Landstreamer and put it on an autonomous vehicle such that we can operate this in really challenging to operate environments, such as if you're out on ice sheets or permafrost or in radioactive contaminated sites. You can just send your instrument off to acquire data and then come back. So in total, that's a couple snapshots of where we're what we're doing here with distributed acoustic sensing at Colorado School of Mines. I'd like to thank you for your attention, and I'd be happy to answer any of the questions that you might have about any of the work that I showed or otherwise. So thank you.
Okay, thanks, Jeff, for the presentation. So the floor is now open for questions. If we have a question, we can just raise our hand and then we will take it from there. But I see that there's actually a question in the chat box, so we could start with
okay. All right, I'll bring my presentation up in just this mode here, and then you can go through that. So in the chat box, there's the chat box. Okay, let's see. Okay, so can you repeat the previous part? Let's see, good to see. 3 questions. Okay, in terms of passive active methods, DAS is exclusively classified as what? Okay, so this is a good question. In this case, it can actually be used for both. So basically, the DAS fiber is fairly agnostic to the types of signals that you put in the ground. So if you wanted to actually use an active source like a sledgehammer, or if you had a weight drop or a vibrosize or dynamite or car traffic, it would basically pick that up. But you can also just use it for ambient background vibrations. So basically, where you don't know where the source is coming from, you can't characterize it, that's when you can actually just use it for ambient recording. So you might want to have different settings on your interrogator for a really loud, concentrated signal versus just sort of weaker background energy. But in principle, you can use it for any of those different types of modalities. Yeah, okay, so how are the mechanical waves being transformed into seismic traces? Yeah, so this is a very interesting thing. So basically, if you have fiber that's, say, elastically coupled to the ground, so if it's like cemented against the borehole, or if it's sort of in very, very compact soils, basically what you have is you have the vibrations coming through the ground that are then being transferred to the fiber. And the waves as they propagate through the ground are mechanical disturbance that have a little bit of amplitude. And what that does is when that amplitude hits the sort of the fiber that's in place, that causes strains on the fiber. So basically you can cause a little bit of extension and a little bit of compression of the fiber. And it's those signals that then once you interrogate that with the laser light, and once you go through that sort of the very first equation that I did in terms of calculating what the strain rate is, that's the data that we're actually plotting. So it has to be mechanically coupled, the ground to the fiber. In this case, in the first case, we were looking at a scenario where we had fiber that was just in PVC piping. And so in this case, the only coupling to the ground is gravitational force. So gravity is keeping the fiber pressed against the PVC pipe. And as the PVC pipe gets rattled, then that basically rattles the fiber that's in the ground. So even though you might not be perfectly elastically coupled, if you're coupled somewhat, you can actually transfer energy propagating through the solid earth or in the fluid earth into the fiber itself. All right. The third question, DAS as an inversion technique, we considered a possible source for obtaining velocity models conventionally. Yes. So there was a lot of work that was initial work that was very interested in horizontal displacement, horizontal deployments of DAS that were on the ground. The idea, they were really hoping that you could take data that basically goes down, bounces, reflects, comes back up. And what I didn't go into here is that the sensitivity of the fiber is actually very directionally oriented. So in this case, if you have a fiber that's laid along the ground, it's sensitive to waves that are causing vibrations in this direction. And so if you have something comes down, bounces like this, comes up as a P wave, it's going to be polarized in this direction. So in this case, the horizontal deployments weren't actually very good for standard reflection seismology. Interesting though is that if you say instead of looking at a surface deployment, if you put energy down a borehole, so if you put fiber down a borehole, cement it into the ground, then all of a sudden it's much more sensitive to shaking in the up-down orientation. So if you have waves that come down like this, P waves that come down, reflect off of subsurface reflectors, and then bounce back up and cause vibrations in sort of the up-down direction, it's actually quite sensitive to those orientations. And so this is a vertical seismic profiling geometry, and we actually see a lot of work out there for distributed acoustic sensing in fiber put in boreholes. And this has led to some really, really high resolution images of the subsurface because they're able to, if you use sort of vertical seismic profiling seismic techniques, you can come up with really accurate estimates of the velocity model, both P and S wave actually, around the location of the borehole. So in those senses, yes, it's actually been used quite effectively for obtaining sort of velocity models in a conventional setting with standard seismic data processing. And this is really being increasingly used for things like CO2 sequestration projects, looking for geothermal projects, and even sort of groundwater monitoring. All of these are very useful for that. I'm not sure if this is being recorded, but, oh, it is being recorded, great. So you can feel free to do that. I'm happy to share the presentation with you if you want to have that and be able to listen to the other things as well. So sonifying, yeah, so sonifying, it's not necessarily an essential technique, but one thing that's a potential downside of DAS is that you can get terabytes and terabytes of information very, very quickly. And so one thing that you can do if you're listening to, say, the low frequencies, you can basically speed it up 100 times and into sort of the typical human hearing range, and you can listen to your data, much, much more quickly than you can scroll through it and inspect it visually. So I think that it's very interesting to so just to listen to the data, but it's not actually a requirement. So specific pre-processing, main processing, post-processing workflow steps. So I think that in the data sets that I showed, sort of the low frequency ones, those were not really standard data that people look at, and so we were looking at how do we separate the kind of dipping signals from the background noise. And so there's a number of techniques that one can use to try and do that signal noise separation problem. Once we get to the DAS Landstreamer data, then sort of we looked at the denoising techniques that involved bandpass filtering, stacking, velocity dip filtering. It really sort of depends on the signals that you're trying to highlight and improve, and that's how you sort of develop what seismic data processing strategy do you want to do that. So yeah, so bandpass filtering, you could do, we did sort of convolutional, two-dimensional convolution. You can then take that in that data and do migration and all the other ones that were suggested there. So in terms of the depth of investigations, there's a couple of key things there. So there's people who have used this for earthquake investigations. So I know in California there's a large fiber array that you can actually use those to measure teleseismic earthquakes coming from the opposite side of the world. You can use that information in order to make images of lithospheric, crustal lithospheric structure. In this case, I would say that many of the techniques that we apply are more limited by the array length that you're actually deploying. So that gives you sort of a maximum aperture. And then also you want to make sure that your interrogator can send signals to the end of it and back and still acquire high quality data. So really, I think that's the main limitations on the depth. The frequencies that we're looking at here, we were looking at with surface waves down to about 500 or 600 meters. Other interrogator designs have better low frequency response, and you can actually get down into the millihertz and be able to get down kilometers in depth. So it's quite interesting that way. We've been on another project where we're looking at sort of putting in boreholes, and we're able to see down to 1.5 kilometers. So quite a lot of depth there. And then the temperatures. So in this case, I've seen, I've done data in sort of higher 40 degree temperature acquisition. I've also done it at minus 20 degrees. So in terms of that, we don't see major restrictions on the temperature regime that we operate, as long as I think you want to make sure your box stays at kind of a reasonable operating temperature. So we don't see major restrictions in that. And dealing with the, so Kingsley asked about the directivity. Yeah, so it's a good question. And there's actually quite a bit of research that's going on in this. And there's a couple different designs that people have used. One of the more intriguing ones is looking at, in this case, you have your main fiber like that, and then people coil fiber around a central one. And the idea is that by having fiber going in this way, and then you have fiber kind of wrapped around in this way, in what they call it helical wrapping, you're able to be more sensitive to the different components of ground shaking. And so that's one deployment on a single fiber you can do. Another thing that people are thinking about is how do we take the actual layout of the fiber and be able to kind of go back and forth in kind of a 2D grid pattern, so that we're basically having the fiber go both this way and go this way, which then allows us to be sensitive to waves propagating in different directions. So that's one of the challenges in dealing with the directivity, and a bunch of people are actually working on that. So I think that's a very topical question. Great. Well, thank you all for those questions. Are there any other questions that people might have? I know we're nearing the top of the hour, the top of the half hour.
I guess so.
So I think there's someone's hand up, Rhythm.
Okay, let's see. Rhythm.
Yeah. So yeah, good morning over there. So my question to you is like, you mentioned about the kinks and the kinks in the fiber and the effects of that on the acquisition part and all. So I wanted to know like, if there are few kinks, and after that, if the fiber is sufficiently straight enough, can we carry out MASW on that part also, or the signal to noise decreases drastically using the
Yeah,
same
so
interrogation?
those are, yeah. So let's say you have a few kinks at the start, and these are sort of not kinks where they're sort of folded over each other. They're where sort of deployments kind of go 90-degree angles, so they're kind of gentle kinks. In those settings, yes. So once you get past those initial kinks, as long as you have a start of like a relatively straight section of fiber, then yes, if you have a section here that's straight, some kinks, section here that's straight, then each one of those sections that are effectively straight, you can use them for MASW.
And what if the fiber has to pass over a culvert via like onboard a bridge or something, where it's not coupled to the ground for that particular 100 or 150 meters approx?
Yeah, no, that's a good question. And this goes back to maybe I'll just quickly share this here. This goes back to this one here. And it's, again, so here, what happens is that if you have a section of fiber that's poorly coupled, then the idea is that in that area, you're probably going to get no information. So here, the data that we're looking at is the difference between those two. And so here, as long as you have a section that falls between x plus LG over 2, x minus LG over 2. So this is a non-bridge section, even though there might be a bridge here, this is going to be fine. You're going to get a good data estimate in here, even though you might not get data in a bridge over here. So it's fairly robust to that, even if you have sections that are not well coupled. And in fact, in many settings, when you're using what they call dark fiber, which someone else has deployed, as you get to the end of one section, there's often like 20-30 meters of just fiber kind of spooled just in a ring, and then they make the next connection splice. And so a key thing that you have to do is you have to go and effectively do tap tests along the profile to see where you are on the ground, where does that correspond to along the fiber length, because they're not necessarily a one-to-one mapping. So good questions.
Okay. One more question I had is, in case of the land streamer experiment with the DAS fiber, so there is no way we can measure, like we can only measure the Z component, not the X and Y. Whereas for MSW, X and Y would be more suitable, isn't it?
Yeah, so in this case, the fiber is going to be more sensitive to ground shaking in the horizontal direction along the direction that you're pulling. And so most geophones are sort of in the vertical component. So it's not it's not the same thing that we're actually looking at in terms of inverting. And there's a potentially actually interesting design that we've been talking about, is how to combine both DAS fiber plus geophone. And the idea is that if you have sparsely, let's say every 5 meters or something like that, or 2-3 meters, geophone spacing that's measuring the vertical, and then you have a dense horizontal fiber, then maybe you can actually use the information on the horizontal fiber to infill denser sampling along the vertical component. So with such a design, we might be able to back out both the vertical and horizontal in a dense sampling along the entire length of the array, and that would be a really nice data set to play with for MASW.
So this is like similar to like seismic high resolution, where we use well log data to pump up the resolution for the Okay. So my one more
Yeah.
question is that
Can I
is
just respond
geo
to that? It's the high resolution. Because this is actually an interesting point, is that the fibers that we're using they're sort of military grade fiber, but they have channel spacings every, we get it down to about 80 centimeters, which of course is less than the log sampling that you have. However, there are also designer fibers that you can build that are, I think, the fiber Bragg grading ones that you can get, sampling down to, only a few centimeters. So you can actually have really, really dense sampling at sort of a centimeter or decimeter scale, down your borehole, which is kind of an interesting thing to think about. Sorry, your next question.
How does sorry, I have one more follow-up question. Like, how does this sampling in the DAS fiber, or like what we call as, I think, zone length or something like that, like how does it impact the length of the fiber serviceable by a single interrogator?
Yeah, so there's a couple different things one has to think about. There's sort of your pulse width that you're actually sending into the fiber. You want to make sure that you have enough time to send a pulse for it to travel to the end of the length and back before you send the next pulse. So things are propagating sort of, close to the speed of light. But if you have a 10 meter, or 1 kilometer fiber versus a 10 or 100 kilometer fiber, then obviously it's going to take 10 and 100 times, twice that, 10 and 100 times, further time in order to get to the end. And so that means you have to decrease your effective sampling rates, you're stacking fewer times, and so your signal to noise often goes down. So the other thing is that as you get from, a 1 kilometer versus a 10 kilometer fiber, every time it's propagating the laser light, it's losing some energy through backscattering back to the interrogator. So if you integrate that loss along the length of the fiber, the further and further your fiber is, the more and more loss you're going to have. So the ends of the fiber tend to be noisier, signal to noise than the beginning.
And how would it compare to like now the conventional, apart from the conventional geophone elements, like now the new MEMS based 3-component geophones are being used. So can we so like in the experiment which you mentioned, where we can combine a geophone with a DAS, I think we can use a MEMS based geophone too, like a nodal receiver.
Yep. Yeah, they're a little more compact, and actually, we're seeing the MEMS like autonomous recording systems actually starting to come online. So instead of having to do cabling all the way back to the central interrogator, you actually could just have them recording continuously the signals in the ground. And so I think combining those two is quite interesting. So I think DAS here is it's really useful in some situations. For example, if you're imaging, or you want kind of a one-dimensional deployment, it's a great dense way to sample the Earth. However, for 3D applications where you want to sample on a 2D aerial surface, then that's where geophones, I think, are still still very useful. So I don't see the geophones going away anytime soon, and I think they have complementary sensitivities and complementary uses.
Okay, thank you.
Thank you.
Okay, so I think that does it for the questions. Unless we have some other questions that we would like to ask Jeff. Okay, then on that note, Jeff, thank you very much for graciously agreeing to do this presentation with us here in the department. We are grateful for that, and we hope to keep the collaboration going.
That sounds great, and you're happy to do this, and maybe sort of wearing sort of SEG hat. I would encourage students in the department to look at the sort of the scholarship program that's out there. There's also the Student Leadership Symposium for the chapter officers of student SCG student chapters. So there's a lot of ways that students, at University of Ghana can come to the image meeting in the U.S. and interact with people from all around the world, and that's how Ellie and I were able to rendezvous at a Geoscience Without Borders sort of forum at Image. So glad to have this discussion, starting up and potential collaboration opportunities going forward. So thanks again for the invite, and hopefully look forward to seeing some of you at a later date.
Thank you. So we'll have the recording of the presentation up on our website, on our social media platforms. That's Facebook, LinkedIn, and X. And I'm sure SEG would also host the presentation, the recording of the presentation on some of their channels, so we can look out for that. So thank you to everybody who joined us, and thank you very much from the Department of Earth Science, University of Ghana, and have a good day.
All right, thank you.